So, um, we are going to start working on two sample things. The next 2 days are two sample things, so it's not bad, I promise. Okay. Two sample T interval. So the first thing you have to do when you do a problem like this, you have to see that there's two samples. Usually that's not that hard to do. And the state is going to be blank percent confidence interval for mu1 equals the true mean something or other, and mu2 equals the true mean something or other else. Just like all of these, if it's not specified, I usually choose one to be the first thing they mention and two to be the second thing they mention, but no big deal. Okay. Any questions about the state? Is that different from what you would expect? Okay, perfect. That's what I like to hear. Okay, plan. The first thing we're going to do is say what we're doing. Two sample T interval for mu1 minus mu2. Okay, why are we doing T and not Z? Proportions, right? So these are means. Means problems, you have to have the population standard deviation to do it, which you won't have. So you have to go to the T. Okay. Random. Okay, so both of the samples need to be random, but they need to be independent of each other. So if you don't like the word independence here because the 10% check condition is checking for independence, separate. You can say random and separate samples if that word is better for your brain and not overusing the word independence. Okay. 10% and 1. And 2. Or I don't have enough room for the or in its own line. Or so either you have to do it separately or there's random assignment in the problem and you don't have to do it at all, which we like better because we're lazy. I mean, at least I am. I don't know about you guys. Okay. Large counts. large counts. Both sample sizes have to be greater than or equal to 30, so CLT applies, or you have to do the graph. You only have to do the graph for the one that violates the condition. So let's say this one's 31 and this one's 29. You'd only have to do the graph for the one that was 29. You don't have to do it for both, just whichever one violates the condition. And we're going to actually practice this today. So anyway, hold that thought. Now, what am I looking for on the graph? Okay, what kind of skew? I'm sorry, what? I'm sorry, I didn't quite get that. Could you be? Yeah, thank you. Thank you. All right, just checking. Okay. Now, okay, so the do statistic plus or minus critical value times okay. Statistic in this case. So when I look at what we're doing, it says mu1 minus mu2. This is the population mean of the first population minus the population mean of the second population. So our statistics should look just like this, except it shouldn't be populations, it should be samples. So you want x bar 1 minus x bar 2. That is your statistic. Taking the sample means and subtracting them. Plus or minus critical value is T star. And then find the standard error on your yellow sheet. You should be able to find him pretty easily. He's right here. Okay, so T star, big square root S of x1 squared over n1 plus S of x2 squared over n2 parentheses. Include. We are blank percent confident that the interval of blank to blank captures the true difference in means of whatever your first thing is and whatever your second thing is. When you're ready, paste in your whole big caffeine situation. Mhm. Are you playing Minecraft right now?
I'm not. There is nothing on, nothing on my guy.
Guys, are you bored? Should I make it harder?
Just for break.
Yeah.
Honestly, I haven't had it in a while. Last week I think I went to. Maybe I should try to. It's so tropical. Yeah, because every time I would buy a box of treasure, it would be like. Thank you. I have a nice week. What? I don't know the last time I bought them. I think it probably.
You're actually not the brightest.
And I was like. Well, I mean, what are you gonna do? My name's not.
Go do next.
It's Albert Einstein. Poland? No, I think he's from Poland, isn't he? Okay, maybe.
Yeah.
I know he had to do some fleeing during World War II. He definitely did some fleeing. Maybe it was to Austria or Poland was the fleeing I'm thinking of, but there was some fleeing. Anyway, hi. Okay. So 20 students were randomly assigned to two treatment groups, caffeine and no caffeine. Dear goodness, please do not place me in the no caffeine group. Each of the 10 students in the first group drank 12 ounces of soda with caffeine, and the others drank caffeine-free, horrible, non-wonderful caffeine-free soda. Sorry, I might like soda. Okay. All students measured their pulse rate before and after. The results are in the table below. Okay. So these are your caffeine pulse rates. These are their change, by the way. These are the non-caffeine pulse rate changes. What are these guys over here? Einstein. Yeah, so this is the mean of all of these numbers. This is the mean of all of these numbers. So somebody already did like the the one variable stats for you. And this is the standard deviation of all these numbers. And this is the standard deviation of all those numbers. It saves you a lot of time when somebody did all that work for you. Okay. Construct and interpret a 95% confidence interval for the true mean difference in pulse rate for students like these who drink caffeine versus those who do not drink caffeine. I brought Einstein today. He was bored at home. Okay. So state 95% confidence dense. I don't know what's happening. Apparently I need caffeine. Confidence interval for mu1 equals okay. So did it tell us what to do? The caffeine first? Okay. Why are the people's pulse rates changing if they aren't doing anything? I guess probably just sitting down or whatever. Alrighty-o, that's done. 2 sample T interval for mu1 minus mu2. Random. Is there any randomness in this problem? Mm-hmm. Okay. Now, random assignment. What does that mean?
10%.
Uh,
You don't have to do the 10%.
yeah. Now, you didn't really have to write this. It's just notes, so I'm going to do it. You could just totally not have anything there.
Not that far, right?
No, no, no. It's just not required. Okay, now I'm gonna flip the page over before I do the large counts condition, and that is gonna be the most annoying thing of all time. So, just so you know. Um, what? Okay. Okay. Here's why it's the most annoying thing of all time, because I need to do either dot plot or box plot for the numbers that are on the other side. I'm gonna do a dot plot just because they gave me like a really nice list of whole numbers, so I might as well. But I'm gonna cheat a tiny bit. The dismayed smiley face is not required either. Okay, so my x-axis for the top one is going to be caffeine. And my bottom one is going to be no caffeine. And what is the lowest number in the table? Not talking about the means or standard deviations, but what's the lowest number in the table? -2. Okay. What's the highest number? Oh no. Okay. So I got my notebook from last year so that I could look at the numbers at the same time as graphing the dots. Ha. Okay. So caffeine 8, 3, 5, 1, 4, 0, 6, 1, 4, 0. Okay. No caffeine. 3, -2, 4, -1, 5, 5, +1, +2, -1, 4. Okay. Do either of these dot plots have extreme skew or outliers? No. And really, you don't even need to look at them, to be honest with you, because you have to keep going with the FRQ. So you just say no extreme skew or outliers, no matter what it is. Yep, you have to, if it's less than 30. Okay. X bar 1 minus X bar 2. Okay. What's X bar 1 minus X bar 2? What's X bar 1? 3.2 minus X bar 2 is 2, so that's 1.2. T star. What's the degrees of freedom in this problem? 9. It's 9. Okay, now real quick, pause. Degrees of freedom in this problem is 9. But what if the sample sizes were different? You always take the smaller one. So make yourself a note over here. Degrees of freedom equals smaller sample size minus 1. Smaller, because you need to be conservative. So if they're different sizes, use the smaller ones. Okay, calculator time. Inverse T. Oh, look, it's already in there. 2.26. Okay, so I'm gonna come out. Here's my formula right here. Okay, standard deviation of the first one. It's 2.7, correct? Over 10. And the other one is 2.624 over 10 also. 1.19. Mm-hmm. Oh, interesting. Well, the chart seems to have a typo. It was supposed to be 2.624. Let's go change him. There, I whited out the little 2. I wonder how many times that's going to happen. Because I just typed these up for this year, so you know how I am. Could be typing anything. Okay, anyway, thank you for asking that, dear. Okay, so all right, so I have statistic plus or minus critical value times standard error. Okay, 2.26 times 1.19. You guys good so far? Make sense? No? Okay, so now I'm gonna put mean, but then I'm gonna go back to the problem and start copying off of it. True difference in mean pulse rate for students like these. Who drink caffeine versus those who don't. Okay, last thing. So you should be able to answer this question with what you already know about confidence intervals. Do you notice that this goes from negative to positive? So is 0 in the interval? Yes. Okay, so since 0 is in the interval, there is a possibility of no difference. We do not have convincing evidence that caffeine increases pulse rate. Okay, what would we have looked for in the numbers for there to be a difference? Yep, all positive. And then you could say, okay, that means that group 1 was bigger than group 2. So there would have been a difference. And it would be very unlikely for group 2 to be more all negative. Yeah, exactly. Just thinking about what caffeine does.